Let's talk about the human eye and vision. There's perfect vision, of course, 20/20, and for our purposes, that's boring. We're going to focus on the more interesting cases of nearsightedness and farsightedness, and specifically how to determine what lenses are needed to correct those types of vision. Now, there are other issues that people can have with their eyes, such as an astigmatism. You'll talk about an astigmatism in lab when you do the model eye lab. We're not going to talk about it right now, other than I will say that it has to do with, for the normal person, the curvature is spherical, but for people that have an astigmatism, it's cylindrical. Otherwise, like I said, you'll talk about that a little bit more when you get to lab. So, as I mentioned, we're going to talk about nearsightedness and farsightedness. And for people who are nearsighted, that means they can only see objects that are close up in focus. For people who are farsighted, they can only see objects that are far away in focus. And we want to figure out what kind of lenses are needed to correct that vision. The eye is a single optic system, so we're going to make use of the optic formula. We're going to start with nearsighted, and what matters here is we have to figure out the person's far point. And what I mean by far point is what's the furthest away they can see in focus. For the person with perfect vision, that's infinity. A person with perfect vision has a far point of infinity, and that basically means they can see the stars in the sky in focus. Somebody who's nearsighted, like myself, can't see that far. In fact, for myself, so it's basically there. That's how far I can see in focus. So we're going to go through how to figure out the lenses needed to fix the vision of somebody who's nearsighted. And we're going to make an assumption here. I'm going to say that the far point for somebody is 1.46 meters. So just pretending we've got somebody whose far point is 1.46 meters, what kind of lens would they need to fix their vision? What we want to happen so that their vision is fixed, we want objects that are an infinite distance away to appear at their far point. So the first part here is the object distance. That's easy. We're talking about objects that are an infinite distance away. And we want the image, as I mentioned, the image of that object that's an infinite distance away, we want it to appear at the person's far point. Now this is going to be a virtual image, so that means a negative image distance. And you might be tempted to put in for the image distance, well, we want it to appear 1.46 meters away, so you might be tempted to just put down 1.46. This would be correct if we were talking about contact lenses. But we're talking about lenses, or glasses, I should say. Glasses don't sit on the eye. This 1.46 meters is how far from the eye. And that's why I say if we were talking about contact lenses, it would be the correct answer to put in here because the contact lens is right on the eye. But the glasses are not. They're a couple centimeters away. We're going to assume they're 2 centimeters away, so we have to subtract that. We have to subtract those 2 centimeters from that, so that the lens is actually going to create an image that's 1.44 meters away from the lens, but it'll be 1.46 meters away from the eye. This part here, 1 divided by infinity, we've talked about that. This is just 0. And so that means we're going to get 1 over f equals -1 over 1.44, which obviously means that the focal length is going to be equal to -1.44 meters. So a person with this far point needs diverging lenses, because that's what the negative means. They need diverging lenses, and the focal length of those lenses would be -1.44 meters. That would correct their vision. Now let's talk about people who are farsighted and how to correct their vision. For these people, we're not going to talk about the far point. We're going to talk about their near point. The person with perfect vision has a near point of about 10 centimeters. For some people, it's better. Some people, it could be as low as 5 centimeters. But 10 centimeters is a really good estimate for what a person's, with perfect vision, what their near point is. And so we want it so that somebody can have something as close as 10 centimeters to their eye, and it still be in focus. So let's look at a situation where we've got somebody that's got a near point of 74 centimeters. That means anything closer than 74 centimeters is out of focus. Anything closer than 74 centimeters is blurry to them. And the purpose of the glass is going to be to take something that is, because we want to get closer, so something as close as 10 centimeters, it's going to create a virtual image at 74 centimeters from the person's eye. That's the goal here. Using the formula, the object distance, we want the object to be 10 centimeters from the eye. You know, that's as close as we want to get. But that means, of course, it's going to be 8 centimeters. We have to subtract the 2 centimeters between that 2 centimeter distance between the glasses and the eye. So the object is actually going to be only 8 centimeters away from the lens. And the image, which again is virtual, needs to be created (74 centimeters from the eye), but we have to subtract off that 2 centimeter distance. When you go through and you do this, it works out that the focal length is 9 centimeters. Somebody that is farsighted needs a converging lens to fix their vision. So people who are nearsighted need a diverging lens. People who are farsighted need a converging lens. And that's really all there is to it.